Good afternoon. We're presenting a project to recover rare earths. We are a for-profit company founded in develop green technologies to be applied in industries. The remarkable magnetic, electrical, catalytic, or luminescent properties of rare earths have long been involved in our daily activities. These elements are used in wind turbines, cell phones, electric cars, and are essential raw materials for the world's transition for a green energy. These elements are currently extracted through mining. They're not remarkably rare in nature, but rather are rarely concentrated into economically significant amounts for extracting and processing. It's very inefficient because extracting even a very small amount of rare earths requires large areas to be mined. On average, only 7 kilograms can be extracted from 1 ton of ore. E-waste can have concentrations over 30% on rare earths, but only less than 1% is recycled. And why? Hydrometallurgical techniques and acid baths are used to concentrate rare earths, producing lots of toxic waste. The recovery rate can reach up to 60%. Also, chemical similarities of rare earths or lanthanides makes it extremely difficult to isolate them from one another. The current concentration and separation process is complex, costly, and toxic to the environment. We've developed a sustainable process to recover and separate rare earths using live saline microalgae. For sources containing rare earths, our technology will remove and separate these elements using a proprietary mixture of dilute mineral acids. After neutralizing pH, marine macroalgae are added to concentrate these metals in their tissues. The final step is the microalgae digestion to recover and purify each of the separated rare earth elements as oxides. An international patent application is now pending on this technology. And why is it sustainable and efficient? Algae grow and capture almost twice its weight in CO2. More than 90% of all reagents are recovered and reused. No toxic effluents are produced, and over 80% of concentration rate can be achieved compared to 60% on conventional mining. What you can see here is our first prototype. We are at a TRL5 referring to bioabsorption, 4 on extraction and selectivity, and 3 on recovery. A TRL7 will be achieved in 12 months with a full-size pilot, followed by industrial scale approach. Looking to rare earth markets, neodymium represents 91% by value of rare earths global consumption, meaning 2.45 billion euros. The market expects to grow more than 500% by 2030 to 13 billion euros. Supply can keep up with the rising demand, leading to depletion of historically accumulated stocks and ultimately scarcity of these critical magnetic materials if additional sources of supply are not developed. Our only immediate source to meet future demands will be through recycling. Currently, permanent magnets are the largest use of rare earths, accounting for 38% of the total market. These magnets convert electric energy into mechanical energy. They're used in electric cars, wind turbines, and computer hard drives. Their composition is mainly iron, 70%, and neodymium, 30%. For its high concentration and availability, this element will be our initial target. A wind turbine needs 200 kilograms of neodymium. A new generation will replace the old ones, which means a large number of magnets will be available for recycling. Having as a source dismantled permanent magnets, we apply our technology to recover and purify neodymium as an oxide. Our suppliers will be recycling companies providing us with magnets. A neodymium oxide is sold through traders at the market price. Our potential competitors have not entered the market and are still at an early stage of development, and their main difficulties is the scale-up, efficiency, and pollutant methods. The project started in 2020 with technology development to identify sources of e-waste, optimize algae growth, and improve rare earths removal from e-waste. We are now in product development doing selectivity tests with our dilute mineral acid protocol. An IP strategy focusing on country selection for registration is also being planned, and in early 2022, we will start scaling up and optimizing so we can enter the market in 2024. 2,000 bioreactors are planned to be built between 2024 and 2026. In the first year, 500 bioreactors will be operational, followed by 700, and at the last 1,800 in 2026. With 80 million in funds, we can start the first phase of bioreactors implementation together with the other necessary operations. At full capacity, more than 100,000 tons of algae can be produced, capable of recovering 5,000 tons of neodymium. Payback is expected at the end of 2024, 1 year after entering the market, and 2028 will estimate a total of 385 million in revenues. To achieve all these goals, a team of 30 motivated members is our engine. I represent n9ve and Eduarda, Daniela, and João de Aveiro University. n9ve has a binding partnership with Aveiro University for the development of this technology. We've already published 15 papers, registered 2 patents, and a P2020 approval for 1.1 million. Our technology will respond to rare earths, global growing consumption through circular use of resources, sustainable products, and innovation. Our initial market opportunity will be neodymium. After building a business, we will expand to other rare earths using the same technology. Thank you.